Thanks for the invitation to talk to you tonight. It's obviously a great pleasure to talk to similar space enthusiasts in Australia. Sometimes we feel reasonably thin on the ground, but so it's certainly nice to speak to people with very similar interests, and it's terrific to be able to talk to you about a journey that I've had when it comes to my space journey. I started off my career, I guess, doing an aerospace engineering bachelor's degree in about 1995. And I went through that, and towards the end of that degree I started to have some real interest in space and some thoughts on how we could perhaps address some of the problems with spaceflight with some spacesuits. So I guess I'll start talking about that and the 15-year journey that has taken us from some of the early designs that we had right through to the success that we've recently had by putting a suit onto the space station in September of last year. So here's the title slide with a few acknowledgements here. Dave Green, David Newman. Dave Green is at this wonderful acronym CHAPS in the UK, the Centre of Human and Aerospace Physiological Sciences at King's College in London. And then David Newman, who was at MIT and who was my professor there for 2.5 years, and who is now the Deputy Director or Deputy Administrator of NASA. And Jonathan Scott and Simon Evans-Stewart with ESA and the European Astronaut Centre, and who were really key in driving this forward. So a lot of my interest was involved in the physical deconditioning that occurs when people go into space, and I think a lot of people are aware of some of the things, but there's certainly a whole raft of effects that occurs across a whole number of physiological systems in the body. This diagram sort of shows a few, but we know that one of the first things that occurs is space adaptation. Sickness, which is like motion sickness, and that's when all your otoliths and semicircular canals get all bunged up, and normally you have a bit of fluid in the bottom of the semicircular canals, and as your body moves, the fluid moves around in those canals and stimulates different hairs and things, but in space the fluid all floats around and stuffs everything up. So you have a very severe form of motion sickness. You have a loss of blood volume and a loss of cardiac tone. You have obviously sometimes higher exposure to radiation. Another thing is that the fluids redistribute, so instead of having your fluids normally sucked down to the extremities of the body, then they just equilibrate all over, and you get much thinner legs. You get this chicken leg syndrome, and you get this puffy face to the extent that sometimes family members of astronauts don't recognise them up in space. So that also causes problems with eyes and pressures and taste changes. But one of the most important things is this weight-bearing bones and muscles deteriorate, and that's because here on Earth we're subject to some quite high loads, and our body is always adapting its strength to that loading environment that we submit it to. So here, you know, when I'm standing up right here, I'm a 75 kilogram, 80 kilogram person. So you know, that seems okay, that's fine for a person, but that's 8 bags of concrete. And if you're trying to lift around 8 bags of concrete, then that gives you a tangible sense that, hey, we're heavy, and our bodies have to be really strong in order to support that weight and be able to move and run and jump that weight all around in Earth's environment. So when you go up into space, all of a sudden, immediately, poof, that's all removed. And the only thing that you need to move around is just the slightest touch on a wall, and then you'll float across. So immediately your bones start to atrophy because they're making themselves more efficient and adjusting to this new loading environment. And you can see that it drops quite a lot. And it's mainly in the weight-bearing areas, as you would expect, because those are the sorts of loads in the weight-bearing areas, the weight-bearing bones, are those that are loaded up when we're standing here on Earth. So we can lose up to 1.5, 1.58% per month when the astronauts are up in space, and that happens almost straight away, and they know that because you can measure the amount of calcium that's in your urine. So you can see that sudden excretion of calcium in your urine. So the key areas here are the weight-bearing areas suffer the greatest loss. The arm doesn't really suffer much loss at all because your arm's sort of normally just hanging around doing nothing, so hanging around in space is sort of a similar type of thing. And then your skull, cranium actually increases in bone mass, and the suspicion for that is that because your fluids have redistributed, now you have a much higher intracranial pressure, and so your skull actually gets thicker because of that greater pressure vessel that is your head in space. So that's the bone loss story, and that's regarded by NASA as I said, as probably the second most severe issue and challenge facing us as humans on long duration spaceflight. The greatest risk is probably radiation sickness in terms of their priorities. So there's a few other things that we need to think about when we look at skeletal impacts of spaceflight. And there's this great one here that it's a great test that you can all do at home, and that is that your stature increases by a significant amount. And one of my professors was Jeff Hoffman. He was one of the astronauts that fixed Hubble in the first lens replacement missions. He's done a number of flights, 5 missions, and on each time they did some stature measurements, and he increased in height by 7 centimetres just in the first few days of a space shuttle mission. So normally, right here, I'm getting loaded and my spine is getting loaded, and it's maintaining a certain length. When we go to sleep, our spine gets unloaded and it starts to grow. And you can measure this at home. I'll show you some pictures, but you will grow by 2-3 centimetres at night. And this is quite well known, and certainly paediatricians know this because they always want to see kids at about the same time each day, so that they're seeing their height growth at the same time and in that same part of that normal daily asymptote back down to your normal height. Then you grow at night, and then you start to get your spine thumped back down by your weight. So doctors always want to see kids at the same time every day, so that they're measuring at that consistent point and they can see the truthful height growth. The problem is in space is that you have this sudden unloading for a long period of time, and you don't have that gentle diurnal cycling that actually keeps the vertebrae and the intervertebral discs healthy. So about 52% of astronauts suffer pain from mild to debilitating, and post-flight they have a 4 times greater risk of herniated discs, which is obviously a big concern, and the British are really taking this interest quite keenly as part of their back and core health program, or the BARC program. And this is really the area that the Gravity Loading Countermeasure Skinsuit, or just Skinsuit as we've called it now, is meant to address. What we're meant to try and do is replicate the normal gravity vertical loading on the body with a skin suit, so that when you wear it in space, you're tricking the body into staying healthy because it still thinks that it's standing in a 1G environment. So if you try and work out, though, what your normal loading regime is, it's actually a bit of a task, because it's not just the same. So the load on my shoulders is equal to the weight of my head and my neck and my arms hanging off them. And as you go down the body, there is more and more and more body weighing down onto that particular point. So by the time you get down to your hips are being weighed down by the weight of your whole upper body. By the time you get down to the soles of your feet, it's essentially your whole body weight. And that's what this graph is trying to show. So for a subject of about 1.7 metres and 75 kilograms, maybe me. Then we had a load of about 150 newtons, or about 15 kilograms on the shoulder. And as you go down the body, then this load gradually gets higher and higher until you get down to the full weight of about 750 newtons at the sole of the feet. So if I was going into space, then I would want my skin suit to reproduce that loading regime to trick my bones into thinking I'm still standing on Earth, and therefore my bones still need to be as healthy as they normally are. So I'm not the only one that's had that idea. Obviously a number of other people have considered that, and the simplest way to try and reduce this loss due to unloading is to try and apply the same loading. So this is a thing called the penguin suit, or the penguin suit. This has been used for decades by the Russians, and it's called a prophylactic body loading suit for bone and muscle. So it's not just intended for bone, it has some other elements here, like these little calf stirrups here, which are meant to put the calf into tension to try and maintain tone in the calf, and some of the more weight-bearing mobility muscles. Essentially what we have here is a suit of two stages. We have a very tight leather belt around the waist here, and above that we have some bungee cords, elastic bungee cords, which is trying to compress the top of your body at a certain loading. And then you have bungee cords that go down to the feet and try and compress that part of your body even more. So you get sort of one stage here and then two stages there. And the reason you have the belt is to try and keep, when you pull harder on the lower stage, obviously you would want to pull the whole suit down. So you need a suit there to try and anchor it to the body so that you can pull the bottom half down harder than what you've pulled down the top half. It's not been a total success, it's never been proven. Astronauts and cosmonauts generally complain quite a lot about it. There's stories that they actually rip out all the bungee cords inside the suit and just wear the outside coverall, because they actually get paid when they wear it. So when the camera's on and they say, look, I'm wearing my penguin suit, and then the camera goes like, oh God, get this off me. So this is a sort of a good starting point, but hasn't been proven. Yep.
Wouldn't that naturally just want to pull your feet up and bend your knees and put you into a uncomfortable position?
Yeah, if it's sort of loose, if that sort of looks loose like that, so it would make it sort of just go like this, but apparently it doesn't.
Is that why you don't often see Russians smiling on space?
Maybe, yeah.
Who pays them to wear those suits? The company that makes it?
I think it's part of their contract. A lot of their work apparently is performance-based. So there are rumours that they get paid extra if they have to manually dock the sleeves. So there's a lot of occasions where I was actually going fine. So, oh no, look, this doesn't look right. Better manually dock it. Get paid more. So. So this is, I don't know why this hasn't come out right, but the dashed line is meant to be the penguin suit loading, and this is my best guess of what the loading is. We don't know exactly. We know it can start at about 40 kilograms. But you can see that the normal loading is this gradual increase here. But the penguin sort of has this top stage, and then it has a bottom stage. So it's not very close to what we'd ideally like. It's either very high here, and when the load is much higher than normal, then obviously you feel that and it's uncomfortable and it can be quite painful. Or if it's too low, then it's obviously not enough and it won't be doing the job, and it won't be reproducing the normal loads that we usually see. So at about 1999 and 2000, I was wondering if we could impose loads instead of just with bungee cords and in two stages, but perhaps we could develop something which resembled some of the suits that were being really successful at the time. Cathy Freeman with the Swift suit and Ian Thorpe with the shark suit. Maybe we can design a suit that has a gradual increase in tension as you go down the suit, which can somehow reproduce that gravity loading regime that we would ideally wish to see. So some of the first concepts in about 2004 as part of PhD at RMIT was to try and design something, and the early concepts actually had a series of compression stages and bands. But then people talked to me and said, why don't you just make it one big piece of elastic, and then each and every lateral fibre can be used as some sort of band across the body, and the vertical strands of the elastic can be used as the loading elements. And the reason why we need to have bands and vertical elements is that if you want to try and maintain this gradually increasing tension in the suit, then you need to somehow anchor it to the body. Just as the penguin suit had that leather belt so that you could have different stages of vertical loading, this suit needs to have lots of belts, if you like, across the body so that we can gradually ramp up and stretch more and stretch more and stretch more as you go down the body. So that's where this concept of bands came from. And then we moved to this concept, which is about 2008, and this was done at MIT when I was up there. And this is the suit. This is actually the suit that Ali was wearing. So you can see she's about my height, I'd say. So you can see that the suit is actually very small. But essentially what it's comprised of is bi-directional elastics. It's very weak laterally, and that's so that you can get into it and out of it, or don and doff the suit very easily. It's also because you don't want to have to try and impose a greater load when you're breathing in. It needs to be quite loose so that you can still breathe comfortably. But the other thing it needs to be tolerant of is body shape changes. And when you start to look at the fluid redistribution, then you can sometimes have a decrease of up to 30% in the circumference of your calf muscle. So the suit has to be almost over-engineered so that it's tolerant to these changes that the body shape may see when it eventually goes up into space. But it has to be very strong in the vertical direction, because particularly just down in here, you're trying to apply about half a G on each leg, half G, then 1 G total. So just this bit of elastic here on my suit, which is similar, is trying to carry 40 kilograms. So the suit has this quite different requirements for the lateral stretch and then the vertical stretch. Another thing that we found was that we needed to have good stirrups and a way of imposing 1 G onto the soles of the feet. So if you just had this stirrup here like this and you just wore the suit, then you're applying 1 G on the soles of the feet through a very narrow area like that. And we found that it was very painful and quite, it's quite clear when you think about it again, but if you stand on, it's like standing on just a piece of metal or something lying on the ground at that same width. So what we had to do was we ended up using cycling shoes which have this thick metal insole. So the stirrup is pulling up on that insole and thereby through the insole pressing on the whole of the bottom of the foot. So it's like the suit is applying a force that you normally have when you're standing on Earth, rather than that very narrow application of force. And we also had a white canvas yoke up the top here. Because it's very difficult to engineer a suit over the top of the shoulders and try and understand the stretch there. And that's something we're still struggling with a little bit. But essentially, we developed a suit which had a much better reproduction of the normal loading regime. So here's the skin suit graph here, and you can see it's a bit higher than Gravity, just at the top of the yoke. and then it stays constant over the height of that yoke, and then as soon as you can start getting a band around the body, then you can start changing the tension down the suit. So that's where we can get it, and we can follow the normal gravity regime all the way down to the ankles. And so at no point are we really significantly higher than gravity or lower than gravity. And we can change this around a little bit. You know, we can start there and then chase it back up a little bit and do all sorts of different things in our reproduction of that graph. But essentially, that's where we started. The other question that I get asked a lot is, well, how tight does it have to be in order to impose this gradual vertical loading regime? And the answer turns out to be really low. It's less than 10 millimetres of mercury, which is less than lycra riding pants. So it's not very painful at all, it's quite comfortable. And what we do, this is actually what's required of the suit, but we would design the actual skin compression to be somewhere up around 15, sometimes up towards 20, so that we have a suitable margin of error in not only our measurements but also in the fabrication of the suit, changes in the body when you're moving around and so forth, because we want the suit to stay at the point that we really want it to. And when we first started wearing it, we found that when we stretched it on and put it on, then the suit all stretched into these various different shapes and it wasn't lying quite where we wanted it to. So we came up with this idea which we've called these stretch arresters, which is quite simple really, but essentially they're these non-stretch ribbons that sit on top of the elastic. And say we needed, because in this suit we actually had to measure each and every centimetre of height and the circumference at that centimetre of height. So it's a lot of sizing and tailoring. But say we needed a 50% vertical stretch here, then what we do is we put 1 centimetre ribbon and sew the ends off at 5 mil of suit. And what that would do is that would allow that 5 mil to stretch to that 1 centimetre, which is permitted by that ribbon that sits on the top, and it won't allow it to stretch anymore. And if we're quite clever, then we can get all those lengths right. We can position these non-stretch arresters down the neutral axis of the body so that we're not preventing movement and inhibiting normal mobility, and thereby try and engineer the suit so that it stays in the right spot and so that it stretches to the design tension but no more. So maybe I'll pass this around if you... If there's any gravy stains, I'll know where
I'm probably jumping ahead, but just a quick one that popped into my mind. You know the G-suits that pilots wear, is there an application to the...
Oh, not really, no. The compressions aren't enough, really, to help that. And also you need an active compression with the G-suits. They only start to really apply pressure on the abdomen and the thighs when you have a high G situation to stop blood from rushing down to the lower extremities. So, there's perhaps an application when we're looking at skin suits for EVA or spacewalking suits, because of that pressure then needs to be far more substantial.
We've accumulated a lot of data now on microgravity biomedical data, so over many years, decades. I've got some folks who've been up there for a year or more. What's the story between a 24/7 application like that as opposed to their actual exercise routine, which is not 24/7? And what does the body really need? Can the body get by with nothing and an exercise routine?
Yeah.
And if the answer to that is yes, how much exercise and how much nothing?
Yeah.
Or do they need a 24/7 suit?
It's not a 24/7 suit.
Well, it's not a 24/7
No,
suit, right?
no.
Okay, so based on what I've said, what's the story?
Yeah, so the wearing protocol is something that we haven't determined fully yet. So there's two aspects to your question. What is the loading that's required, and what is the protocol that this suit is worn at? As you correctly state, you're not standing up for 24 hours a day. Therefore, we don't have to reproduce that loading regime for 24 hours a day. Where our torsos are upright for maybe 16 hours a day, and depending on your job, then you could be standing up for almost 16 hours a day, or if you're in an office, then maybe you're only standing up for 2 hours a day. So what we started to do was we started to look into, we started to look into the daily metric, a sort of Newton hours, if you like, of the standard person or a standard astronaut type. And in that way, what we could do is try to reproduce what some people call the daily bolus of loading. So the torso needs 16 hours of 1G, maybe your legs need 4 hours of 1G. And if you can apply that, then you're reproducing the normal amount of newtons as you would. So, but you can't sort of wear a suit for 4 on your legs and your torso for 8. So then maybe what you do is you wear, instead of 1G for 4 hours on the leg, maybe you have half a G for 8 hours. And then your Newton hours at the end of it all is still the same. So maybe you have 1G torso, half a G suit, and that's an appropriate reproduction of normal loadings. The other idea...
So is Newton hours the actual parameter in the sense that it doesn't matter how many newtons? Once you determine the newtons, you determine the hours and vice versa? So the body takes a note of Newton hours, does it?
Well, this is one part of it. So the answer is that just standing up is not the sole loading condition that our body has to address. In fact, if you just stand up all day, you won't stay healthy. So what we have here is sort of static loading, which is sort of 1G and constant over a long period of time. And then when you're walking around, you have this short duration impact loads, very high. And so when you walk, run and jump, you have impact loads of, or you have loading through your bones of 3, 6 and 9 times your static loading. Some people believe that it's probably these transient impact loads which are really telling your bones how strong you need to be. And then other people say, well, you need the combination that you have on Earth. I think that we need to have a combination, and I think we still need to do exercise, and that this suit will hopefully form one part of a whole countermeasure suite that will be used in the future. So one of the things that this suit can also do, though, is assist in the delivery of those impact loads to the normal scale that we would have on Earth. And the reason I say that is because astronauts do hours of running each day on the treadmill. But the harness that pulls them down onto the treadmill can't pull them down at 1G. So they're not getting the same benefit from running. They're not getting the same loads through their system as they would on Earth, even though they're doing all this exercise up in space. There's a similar aspect when they're riding on the cycle ergometer, because it's quite difficult to sort of stay on the cycle, and you're sort of floating around a bit and you sort of pull yourself down. So the suit can actually form a very good harness in that you have a full 1G connection at the stirrups at the base of the feet. So what we've been considering is a harness system which pulls the feet down onto the treadmill at 1G. So what you're getting is the normal static loading, plus with the treadmill you're getting the full normal impact loading that you would get on Earth.
Right, so you can do your treadmill work in 1G.
Yes.
Right.
The other thing that we're looking at is do a lot of cycle ergometry in space, and one of the things that they do is they put little shunts in it and make it sort of quite staccato like this, so your cycling goes bang, 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 bang like this, and each time it clicks over it sends an impact through the body and then tries to reproduce some of that impact loading. But that's not a very nice thing to try and use. That's trying to ride a square-wheeled bike, it's not very nice. The other thing that the suit can be used for is that there has been some evidence to suggest that vibration can provide stimulus to bone and maintain bone density. And particularly I've done a lot of tests with turkeys the last time I was looking, and they found that turkeys can maintain bone density, and they're trying to reproduce that model into humans. But obviously it's very difficult to try and apply vibration in space, because you can't just stand on the plates like you do in your 1G lab. So what we can do is we can design the stirrups so that they go around vibration plates, and then they force that vibration into the soles of the feet, and thereby reproduce the same conditions as they've seen successful here on Earth. So the suit applies sort of that base loading, and then in concert with other countermeasures, you can reproduce that impact loading.
What about dietary calcium supplements?
They don't work. Excreted straight out. Body doesn't need it. Straight through. And in fact, that can be even more of a problem, because you get things like kidney stones.
Right.
So, when you have all these minerals going through your system, and they can aggregate and get kidney stones, and so that's obviously the last thing you want in there. So there's a lot of research into pharmaceutical treatments, and all sorts of different chemicals to try and take and try and trick the bones into staying healthy. And there's obviously things like big centrifugal ship designs and all sorts of things.
Was it, I think, Skeletal, I don't know if the early Russian space stations did it, it's got a lower body negative pressure device.
Yeah.
Like an iron lung.
Yeah, LBNP is a device which encloses the bottom of you in a lower pressure, and I've done it with you use a kayak seal around you here, and it sucks you down onto a treadmill which is inside that same container. It's quite effective, and in fact they use it quite often in bed rest studies here on Earth, because 6 degrees head down has been found as quite a good mimicry of spaceflight. So there's a lot of people doing bed rest studies where they get subjects and they lie down 6 degrees head down for months. Unbelievable. For everything, going to the loo, going to the shower, eating, you name it, for months at a time they lay down 6 degrees head down. So it's not even lying down, it's head down, lower than your feet.
So lying on a surface tilted 6 degrees downwards?
Yes. Yeah.
Hospital bed with a head down?
Yes.
Yeah. Sounds like fun.
They do all their exercise and get maintained.
Right.
And all the students love it. It's, lie down and watch movies all day, sign me up and get paid for it. I'm all over this. But after a few hours, when they've seen The Simpsons, I'm not interested anymore.
So is this just a skeletal program, or has it got cardiovascular benefits as well?
We think because of the increased resistance to motion, the more effective harness, then perhaps it would have some sort of musculo skeletal impacts as well, but it's mainly just skeletal at the moment.
Because part of the lower body negative pressure devices was to get blood to drain down.
Yeah, well, part of the attraction is that it starts to suck the fluids back down into the normal regime, where it's down higher pressure down at the extremities, and that's shown by why you normally take your blood pressure here, yeah, because that's at heart level, which is where you want to know the blood pressure. So if you take your blood pressure doing this, then it's a lot lower, and if you take your blood pressure down at your ankles, then it's a lot higher. That's why giraffes have really thick vascular systems around their ankle, that thick. So in space, obviously, you can take your blood pressure anywhere on your body, because it's the same everywhere. But LBNP is used to the Russians have an LBNP suit. It's called the Chivas Suit, which is essentially a negative lower half suit. And what that tries to do is acclimatise the body into the fluids getting sucked back down to your lower extremities on your return to Earth. So it's trying to acclimatise the body and get it dressed down so that you don't faint and fall over when you first get down there. And that's especially important for shuttle pilots and stuff like that as well.
Quick question, you say it's like approximately 3 kilograms. I think that's half a kilo.
No, so when you add the shoes to it,
Okay.
and when you add the other things to it, so...
You talked before about the total number of mutant hours of force applied to the body.
Yeah.
You could apply half the force and twice as long, things like that.
Yeah.
What about twice the force or 4 times the force for a quarter as long or an eighth as long? Or where does, have any studies looked at, in fact, the reverse of that?
In other words, is it linear?
And I can imagine you could just do exercises that maintains force in your body, you know, just by pulling against something with your feet like in a gym.
Yeah, you can.
And you know, you can sustain far stronger loads than you normally would, but for a shorter period of time.
Yeah, so there's a device called the Advanced Resistive Exercise Device, or ARED, which is based on that premise, sort of imposed resistance devices. It's a big thing. You know, if you look it up, pictures of it's like this sort of home gym in space, and there's lifting up these big hydraulic things and all sorts of stuff going on. Apparently that is quite effective. But when we're looking at these sorts of vehicles that are going to take us to Mars and the Moon next, there isn't space for that. There isn't space for those sorts of devices. There obviously isn't designs for, tethered spacecraft and artificial G environments. So that all of that is leading to some of the benefits that this suit can provide, in that it's so light. It is quite cool and comfortable. I can vouch for that. It's very cheap to produce. It requires no power and produces no vibration. So all these treadmills and cycle ergometers and big ARED devices and so forth are very large, expensive to get up there, require power, need to be isolated from the station, because obviously if you're thumping on this treadmill all the time, then solar panels start to flex and all sorts of very sensitive experiments that are going on in the rest of the station get affected. And what's really crucial, what I think is a real benefit to this, is that you allow the astronaut to get on with normal work while they're wearing this treatment. In fact, one of the applications that we thought would be really great is to wear it as a pair of pyjamas. So work out what you need. If you have an 8-hour sleep, then let's work out what the Newton hours are for 8 hours, design the particular loading regime, and there's your set of pyjamas. There you go.
Would you get to sleep?
And I don't think you would, because I'll show you we did some work on some sleep studies, because we wanted to look at our spinal elongation. We did a study. How much do I normally grow at night? And then how much do I grow at night if I wear a skin suit pair of pyjamas? And if we could show that my height elongation was reduced, then we have some evidence to suggest that, hey, this suit is actually doing something physiologically to me and maintaining my spine loading even when I've unloaded it and sleeping at night. So I couldn't wear it all night. It was too painful. It's like trying to sleep standing up, because you have this load on your feet. It's like and after 4 or 5 hours, I slept, but then I woke up after a while, and you want to try and just take the load off, and you can't. It's this incessant loading on your feet. You're trying to kick it off, and you can't just stand on one foot and release it for a while. I was going to say nasty things to the designer, and then realised that was me. My wife was in the study too, and she was hitting me saying, "I hate this thing, James. I'm not wearing this." And,
it's not too bad. Some scientists have to inject themselves with polio and effectiveness.
Well, it wasn't quite a Marie Curie moment, but I'm being quite honest here, aren't I? It's all getting recorded. This is all going to go down in the archive against the suit. But we have a way to redress this in the future. So it can be, the other exciting things can be configured for orbital, lunar and Mars conditions, and by that I mean it can gravity fill. So if you're going to the moon for a period of time, then maybe you want a suit that will provide the 5/6 gravity that fills from your 1/6 that the moon is providing. It provides 5/6, so you get a normal 1G. Or if you go to Mars, you have 3/8 from the planet, and then you have 5/8 perhaps that the suit provides, so you get a normal 1G on that surface. So,
but do we know how the skeleton reacts over the whole range from 0 to 1G we make a statement about 16% and about 38%. We've got absolutely no data on Mars gravity biomedically at all, it's zero. And for the moon, we don't really have data. I mean, we've got 22 man days on the moon, but they were bookended by 4 days of weightlessness going and coming back. So there were no measurements taken the instant they landed and the instant they took off from the moon. So we've really got no lunar data either. So do we know, maybe in 16% G, the skeleton's okay, or do we know that it isn't? Maybe in 38% G, the skeleton might be okay, or do we know that it isn't?
Yeah, hold that thought. I would disagree that we have no data on that though at the moment. We've done a range of mice studies that have flown and been spun to produce gravities that would reproduce lunar and Mars conditions. So that was actually my roommate in the States did some of those studies, which is probably a bit more than the scope for this talk. But if you hold that thought, I'll address some of that later on, I think. Yeah.
I'm assuming there's no fashion criteria for these things.
What are you suggesting?
I'm assuming that there's no
Come in any other
criteria.
colour.
I'm assuming
You wait till you see my white one.
there are fashion criteria that you have to.
We had a number of really high criteria for the astronauts to wear. I'll get to that too. When can I go until? I actually appreciate the fantastic questions, by the way. Can I keep going? Okay. I think in answering some of these questions, I think I've addressed some of these points on here anyway. So the first, this is the Mark I suit, about 2009, and this was the first Parabolic Flight campaign that we ran out of Florida. And there's the white one that I'm sure you'll appreciate as a height of fashion here. And one of the things that I learned quite quickly was that white elastic goes transparent when you stretch it.
So is that good or bad?
That's, well, it's,
What is it?
so it was funny because I was looking around and saying, how am I going to make these? Where can I go to get these made? And I almost was going to call up one of these latex suit, kinky things, whatever, body suits, whatever they are. I thought, no, there must be a better way. And I bought the material that I thought, and they didn't have blue, and I always made my suits blue, and they ran out of blue, and I had to buy white, and I was like, oh, how is this going to work? And then I ended up finding this place called Costume Works in Boston. And they said, oh, you'll come around and let's talk to it. So I drove over there with my white, elastic under my arm, and I said, look, I want to make this crazy suit that's going to apply load to the body. And I walked in there was all this blue jumbo spandex, which was the stuff that I really wanted to make. And I said, well, you bought all my spandex. And they said, yeah, we're making Power Ranger costumes for Disney World in Florida out of it. And I said, oh, I've come to the right place. You guys know how to make jumbo spandex suits. But unfortunately, they didn't have enough blue left over, and they had to make one suit out white, and it went transparent, so I had to be the guinea pig there and be considerate to all of our subjects there and wear a suit that didn't go transparent. So you can see this is the Mark I. You can see we've got all the stretch arresters down the side here. Zipper on the front. First time you fly a Parabolic Campaign, you have to have your name tag upside down, apparently. And then if it lands, you get to turn it the right way around. And then what we've got is all of these horizontal lines across the suit. And the protocol that we had was to try and measure these lines so that we could measure the tension in the suit at all the parts of the body, and in that way determine on this flight whether the suit was stretched to the design strain that we really wanted. So here's that suit up in space, and one of the things that I saw after is that she's got her hand here on the emergency release. And I'm sure it's fine, if you can't just release it, but I think I would have been more nervous had I noticed that at the time. And that's Dava there behind.
Did you have any electronic sensors in the suits at all?
No, no, we didn't.
So it's all mathematical?
So we were just trying to take it, manually with the tailor's tape, which this had 6 lunar, 6 Martian, and 8 micro G parabolas. And I've got a video which I can show if we've got time afterwards to show you what a standard parabola is and some of the highlights from the whole trip. So I better start moving through this pretty quickly, I guess. But we had 3 subjects, and essentially we found that the torso strain was bang on where we wanted it to be. The thigh strain was pretty close, but we were really low on the shank, so the design was inferior on the shank. And otherwise, we found it was pretty good. Comfort was good, and there wasn't much of a mobility hindrance to that Mark 1 suit. This was the Mark 2. We made some changes. We had additional stretch arresters, mainly to try and address that shank issue that we had where the load wasn't quite high enough. This is 2010, 2011. This is my wife actually, and this is a device called TechScan, which are very flexible, thin pressure transducers, and we put them inside the shoe, and then we could measure on here the type of force that was being applied to the soles of the feet. And we still had a 1G design here, so we could see, are we actually, if we add up all the little pressure transducers, are we putting 1G on the sole of the feet, and is it applying this sort of force? And this is where we also did the sleep study with that suit. So Mark 3, this is where King's College really got involved, and the European Space Agency really got involved from this time onwards too, because it would have been in about 2009, I guess, just rewinding a bit, that they attended a conference at MIT where I was a postdoc at the time, and we started talking about new technologies and new designs to try and apply the sorts of loading to the spine, which is what they were really concerned with at the time as part of this BARC program. So they were saying put some funds in, and King's College is at CHAPS, Centre for Human Aerospace Physiological Sciences, was doing a lot of work to try and test the suit physiologically to see if the suit was actually doing what we said it was doing, and whether it would apply some sort of advantage to the suit as well. So that was the Mark 3, and they found that we were having some quite good loading at the feet and the shoulders, little effect on range of motion and ambulation and other exercise metrics. They did find it was quite uncomfortable and had limited durability, especially with some of these elastics. You stretch it maybe 10 times, and then hysteresis, it doesn't quite return to where it started, and then it just starts to get weaker with time. So we had some new goals for the Mark 4, which we went through, and then we got on to the Mark 5, and this is about 2014, early 2014. And this is Thomas Pesquet, who's one of the ESA astronauts, and Dave Green, who's the professor at King's College. And what we had by this stage was a realisation that Costume Works probably wouldn't be able to keep making these suits for us. We needed to go somewhere a bit more professional. And they were quite open and said, look, it's been a great ride, but we need to hand this over. And there was also an impetus to try and keep as much of a European input as possible. So we ended up going to an existing relationship that MIT had with Dietary, which is the company that makes the motorbike racing leathers. Valentino Rossi, if anyone follows the racing, they're the people that make those form-fitting racing leathers. So they have some good experience with making these form-fitting performance garments. So we had the Mark 5, some were made by Costume Works and some were made by Dietary, and we had some handover at the time. And we did a Parabolic Campaign run out of ESA, this time out of Toulouse. I think it's Toulouse. And you can see there's all these nets here, which I'll bring up in the video. But Dave Green was saying that the French astronaut was sort of, flying around and going, wee, like this, and then, and he was saying, well, that means yes. That means yes in French. So the suit's selected. We can fly it now. The French astronaut says it's good. So that was actually an assessment for whether we should go ahead. Is this thing just a silly lab experiment, or is this something that's legitimate and we should test more? And the answer coming out of that was yes, and that we. Sorry?
It was we.
Yeah, he was going we, and yeah. So then we developed the Mark 6, which was then another small improvement on the Mark 5, purely made by Dietary this time. King's College did a few more experiments with it. Here are some results, but we found that there were significant differences in the height increases in this hyperbuoyancy flotation. This is lying on a bed, but there's actually saline water. So you actually have a very effective unloading of the spine, and you can see changes in spine length very quickly. And compared to normal or gym clothes, when you wear the suit, you get a reduction in the type of spinal elongation. That still shows an elongation, yeah, so it can't be working. Well, what we did was we reduced the suit from 1G to 0.2G. So this is part of our experiments to try and work out what sort of loading do you really need to try and keep people healthy. The other thing that we were trying to explore is what sort of loading is tolerable to someone wearing this for a long period of time. And we found that 1G was just a bit too much on the body. And obviously the lower the G we went, the more comfortable it was. So we thought we'd do a 2G test, or Dave did, and found that we got significant results not only in trying to reduce the spinal elongation, but also in terms of pain indicators. So we got far less pain in subjects when wearing the suit compared to just wearing normal clothes in the cervical and lumbar spine. So the suit was selected for a short duration ISS assessment to be worn by Andreas Mogensen in September of last year. We had to do a whole range of preparations a long period of time before that flight, obviously. Some of the concerns were that we had to measure his dimensions many months before the flight. How would we know how he would change on the actual flight? We also had to go through extensive flight certification. One of the things that the guys at the Astronaut Centre had to go through was confirmation that you could get out of the suit in 30 seconds, which was part of the emergency protocols that they normally have. And there was some argument that this suit is so form-fitting that you could still get in to the so-called Russian emergency suit, a launch and re-entry suit, without having to take it off, but nonetheless we couldn't show that you could get into the so-called with it on, so we had to still comply with the regulation. And the guys over in Cologne at the Astronaut Centre had to do all of this sort of stuff. And they also determined the protocol, which was to evaluate the ability of Skinsuit to counteract spine elongation and lower back pain, to try and prove that some of the tests that we had from those hyperbuoyancy flotation tests were actually justified and true, to try and measure the G-load with some, it's called force shoes. That's what these are. This is like a more integrated version of that TechScan pressure transducer array in the suit. Evaluate operational considerations, you know, like can you go to the loo, can you get it on and off, is it comfortable, can you move normally, and evaluate the effect of wearing a skin suit while exercising. So in September we went over and we went over to the console to see the astronaut wearing this live on the TV downlinks, and this is the sort of stuff we saw. He didn't sort of wear it and dance around and proclaim. You know, they have these schedules which are extraordinarily precise, you know, down to minutes, and they have this red line that just keeps moving across their bar, and they have to keep ahead of the line. They've got many things going on at the time, so we were sitting there, and then the TV came on and he was wearing the suit. So it was a fantastic occasion to see it being worn in space. And then he actually tweeted this photo on one of the days. So he was meant to wear the suit for 3 or 4 days, but then there was a problem in getting in the Soyuz flight up to the station. I think there was some orbital debris changes, and he only had a reduced time on station. So at one stage, Skinsuit was completely off the agenda, and then they put it back on, and we had reduced time, and we didn't go through all the studies that we wanted him to go through. But essentially the outcome was, yes, it was comfortable and he can do all sorts of stuff. And there's a few issues that we need to address. There's always things that we want to improve. As engineers, that's, I guess, what we do. We just want to make things better. But essentially it was a success, and we didn't know about that at the time. You know, he was just wearing it, and we sort of said, oh, that's great. But in the months that followed, when we debriefed Andreas, and we discovered all these things over at the AC. So the future work, we want to focus on the spinal loading. So instead of a skin suit, we're almost looking towards a spine suit type of arrangement where you wouldn't have stirrups at all. It would just be loading up the torso, and then maybe some leg components where you're trying to balance that load. I think that's quite an interesting modification to it. Improve the measuring and fabrication. We're looking at 3D scanning and sort of stuff, because we're getting inconsistencies in different subjects and measuring people and the astronaut differently, and we get different, measuring sizes and stuff. Improve the design, determine optimum G loading. We had success with 0.2 G. We think we can ramp that up while still maintaining the acceptable comfort that we have now. And then, I guess at the end of the day, we wanted to go into a long duration ISS flight. We wanted it originally on Tim Peake's flight. He's up there now. Because it's British, it sort of fed back into some of the British aspects of the back and core health program. But that was too soon after Andy's flight, so we hope maybe Thomas's flight that's launching in December. There's a lot of acknowledgements to make. Obviously, I think I've mentioned a lot of these guys. Paul Webb was a big inspiration, and he unfortunately passed away just before the flight, so that was an awful shame that he never got to see these sort of skin suits flying in space, because he's been working on some of these technologies, principally for EVA suits, not for IVA, for extravehicular activity, not intravehicular activity suits, but he's the master when it comes to space activity suits and skin suits. And here's a comparison. That's the Mark 1, it's the Mark 3 and the Mark 6. You can see it's quite different. Dianese materials, different colours. The astronauts wanted they didn't want bare shoulders, so we had to incorporate a t-shirt element into it, and other aspects like that. So it's been a journey, and something that's been really satisfying to see it go into space, and hopefully we get to see it go up into space a bit more and be part of future long duration missions as the countermeasure suite. So thank you.
Thank you.
Were you able to test if you could get in and out of the spacesuit? Was it on? Or was that not on the feedback thing altogether?
Yeah, that was on, and he could get out of it. Did you want to show the video?
Yeah, let's do that. Yeah. We'll do you want to have just a couple of minutes for the video and a couple of questions if we've got time for that? Do you want to do the video?
Cool. Just a question. For as long as I can remember, the plan for interplanetary travel was artificial G.
Yep.
Why has so little research been done on manned artificial G?
So there's a number of ways to apply artificial G beyond just wearing a suit, and all of them are large and expensive, and I guess one of the things that was certainly happening in the lab at MIT was this sort of artificial G cycloergometers, and you sit on an arm and you start cycling, and it takes you these big circles. There's also short arm centrifuges where you sort of have your head near the pivoting axis and your body sort of goes around like this. And then there's the tethered spacecraft and rotating large annulus spacecraft. They're all just really expensive. And if you've seen the Constellation or the Orion, architecture, it's tiny. There's no space for any of that. So This is where hopefully the skin suit can address it, because it's so simple and it addresses some of those artificial genes.
You did talk about a suite of things, so
Yeah.
a suite of things would lend itself to expense.
Well, I think, I envisage skin suit being worn with cycloergometers, which is quite simple, being worn with vibration plates, being worn with some sort of pharmaceutical supplements. That sort of order of things, not all the big, I don't think you need A-Red, although that's quite effective as well. But
Is it this one?
yeah, you do that one.
Any plans for a hood?
So James,
Astronaut won't wear a hood. They don't want to wear a hood. We asked that, but
so what can you say?
okay, so this is inside the Parabolic Flight Campaign, the first one we did in about 2009. We maybe turn. So this is when ESA saw this, they were horrified that there are all these people sort of floating and dancing around, all hitting each other. Because you notice that, you remember the photo I highlighted, the netting, and every single experiment has their own little netted off little area, and here they're just thrown into a big old cargo plane that was doing these parabolic flights. And we had people with laptops and expensive equipment doing all sorts of other stuff. And there'd be a ball of water that would flow, and oh my God, this thing's going to just, as soon as we pull out of the pitch over, this water's going to all over the laptop. And amazingly, we didn't have anything happen. But we were sort of stuck in this part of the cabin, and there's me in the white suit, and we had two. There's Ali wearing the suit I brought along tonight, and here's where we're trying to take photos and trying to put the tape up against the body and trying to measure the distances between those lines on the suit so that we could determine the tension. So at the moment I'm still standing. So I think we're still in the Lunar. No, we'd be in Martian. So 3/8 was the first one. At Martian we got maybe 20 seconds of Martian G, and then when they pull out of the pitch over they go, get down, 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 because when they pull out it's quite violent, and if you're still floating around, you just bang right down into the ground. So then you get down and you lie down and you look up at a point in space, because it's the pull-up, which is about 2 Gs, which is actually more nauseating than the floating part. So here we go, this is the start of micro G. And it's so ridiculous. I nearly had a man hug with him, and I pushed off. And you just keep moving. You don't stop. It's incredible. You try and stand up, and you just keep floating up and hitting yourself into the ceiling. So this was a bit of a violent pitch over, a bit less than 0 G, I'd say, on this one. You can see people just floating around. It's like chaos there. But you try, and then at the start of it they said, so who here thinks that if you try and start swimming in micro G it's going to make any difference to where you're going? I go, oh, who's silly enough to think that? That's ridiculous. No one thinks swimming is going to... But the first thing you do is you try and you start swimming.
And what happens? Nothing.
Oh no, you just look. All you end up doing is you just kick people around you. You're trying to dog paddle your way around, and you end up just kicking people. And we were meant to be trying to measure the tension in a micro G. When we could still stand there, it was okay. But as soon as we started floating around, all bets were off. It was ridiculous. So this is science somehow. Yeah, it was great stuff.
Is this a commercial?
Yeah, so this is 0 G.
Commercial 0 G company?
Yeah, it flies out of Titusville.
Were these people here mostly tourists? Or?
No, these were all MIT people.
Because a lot of them just seem to be just jumping around and doing nothing.
Yeah, and on cheesy grin. So they're all people, and they all proposed to do experiments on this flight, and that flight was dedicated to an MIT range of experiments. And some people were on there, just to make sure that it didn't float away, or some of them only had an experiment for the Martian G. So for the rest of it, they didn't have anything to do except blow balls of water down the.
So what's the future now? What's the next evolution? What's the next phase?
Oh, probably those things in the future work. Address each of those things individually. Spine suit.
So what can you say about lunar loadings and Martian loadings?
We didn't expect to see any change in the tension of the suit during those various regimes, and I can't tell you what we saw for micro-G because we didn't get any real data out of that. But what do you mean in terms of how it feels like?
We know what the human skeleton does. Does it need some compensation in lunar loadings and Martian loadings?
Yeah, so
we really only have 0 and 1. We've got very, very little or next to nothing in lunar or Martian.
Yeah, we have some knowledge of the mice, but no, we don't.
That scales.
We don't have all the answers.
We've got no human data at 38%, and we've got very limited data at 16%.
That's right.
So, do we know? Does the skeleton need loading other than 0, or does it need only 1.0? What does the skeleton?
Yeah, I don't think we need to exactly reproduce 1. We found really good results at only 0.2. So we think that there's some kind of balance there.
Well,
but we don't have the answers to
If you've got good data at 0.2 and you're on the moon at 0.16, do you need anything? Do you need a suit on the moon?
Maybe not.
And therefore, do you need a suit on Mars, which is 0.38?
Can't answer that.
So
But-
we actually don't know.
But
We've
we
got
think
no
we
biomed
do.
data on humans and Martian gravity, and very limited biomed data on humans in lunar gravity.
Yeah.
We've got another 30 or 40 years to work that out.
Yeah, and you've got to get there. So
You've got to get there.
Sorry, on that basis, one of the factors, you've done this project work at higher altitudes.
no.
No, I mean, like, instead of having 1G, you've got only something towards that, like in high altitudes.
Yeah, no, we do hypogravity simulations on the bed. So that's all we do.
Just a question, a slightly different question. How do you work now for BAE here in Australia? What's your capacity in relation now in your current job, profession, to work on the project? I'm just curious how a person in Australia can work on anything related to spaceflight.
Yeah, so my day job has got nothing to do with this. So my day job is managing corrosion on F-35s.
Oh, is that all?
Because obviously we don't have jobs like this in Australia. So there was sort of my industry and day job part of my career, and then my academic side of my career. And at the moment I'm a co-principal investigator of this effort. I've been retained in that capacity on this program. And I'm also I guess I'm here representing RMIT, really not BAE, as a senior research associate of RMIT. But it's quite difficult. So I don't really spend a lot of time on this. They'll say, what are your thoughts on this, or where should we go from here? And that's really my involvement now here in Australia.
So RMIT has some funding in this area from ESA?
No.
So you're working for ESA almost as a charity?
Yep.
This multi-billion-dollar organization?
I've been to Europe twice, and they almost pay for the cost.
Good
Well,
enough.
yeah.
So my second question was going to be different, assuming that there was something going on in Australia to do with spaceflight, but obviously there's nothing.
Yeah, I'd like to change that. There's a number of ways that we can add to this program at RMIT, with the Centre of Advanced Materials and Textiles and so forth, and I'm trying to get that in. There's 3D scanning, which is one where we want to go, and RMIT has expertise there, and materials and perspiration wicking and all sorts of different things that we can try and improve the suit design here locally. But at the moment, it's I guess I'm just trying to be involved and pursue it because I've been in it for 15 years. So,
It's really sad,
yeah.
unfortunately.
Well, the stars have aligned. It's all going to change from tonight.
Oh, great.
Yep. This is a perfect segue to our presentation, which happens after our break.
Mm-hmm.
We have a guest coming in via Skype from Perth,
Yep.
who's trying to establish the Australian Space Party to try to get some actual attention to the benefits of Australia having some sort of focus and attention to space and spaceflight technologies. One of the agendas you'll hear about it is perhaps establishing an Australian Space Agency of some description.
Yeah.
And to me, it seems like this could be.
Well, there's Australians working at EAC. Andrea Boyd is ISS Flight Operations over there, and there's another Australian over there. I met John Cherry, who's a medical doctor and looking at biomedical engineering and flight surgeons. There's Aussies wherever you go. So.
Well, once again, thank you, James, for coming tonight. Really appreciate it.
Yeah, no problem. Thank you.
We're going to have a little break for socialising. You probably get some questions.